Today, I will explain variations on gradient descent. Before that, I want to recommend a very important book that I used as reference for all my slides, Learning Deep Learning by Magnus Ekman. I really highly recommend this book if you want to dig deeper in deep learning. So in previous videos, we saw how we adjusted the weights using gradient descent and back propagation. We were implementing a special case of gradient descent known as stochastic gradient descent. When we talk about gradient descent, we would compute the partial derivatives of all training examples. However, we did a single training example. Computing the derivative for all training examples is also known as batch gradient descent. That is, we would to evaluate a full batch before we do the weight adjustments. While if we just do a single example, we get an approximate value of the gradient, and we call this stochastic gradient descent. There is a trade-off between accuracy and computation. If we compute the gradient for more training examples before we adjust the weights, we will get more accurate adjustments. But if we do more computations before adjustment, we will slow down learning. A middle ground is the best. We want instead to evaluate a small number of examples before we adjust the weights. This is known as a mini-batch gradient descent. Mini-batch gradient descent works very well on modern GPU hardware. A GPU can compute a full mini-batch in parallel as long as the mini-batch is of a reasonable size. Therefore, the time between weight adjustments is not affected by if we do a single example of or a full mini-batch before adjusting the weights. Apart from the number of training examples between adjustments, there are other tweaks that we can use to the gradient descent algorithm to enhance learning. In our basic gradient descent algorithm, we computed the gradient and adjusted the weight. We used a fixed step size, and then we looked at the next gradient. There are two key modifications that we can introduce here. The first of all is the momentum. This will consider not only the current gradient, but also the values of previous gradients. Let's take an analogy. Think of a ball rolling down a hill. The ball's direction will be affected both of the slope in the current point as well as the momentum that has built up based on previous slopes. The second modification is that we can adjust the step size over time. There are several ways of doing this. In deep learning framework, we will use something called optimizers to choose between these different alternatives. If we want to just use the momentum, we can use a feature known as Nesterov momentum. If we want adaptive step size, we can use the ADA grade or RMS probe optimizer. If we want to have both momentum and adaptive step size, we can use ADAM optimizer. I recommend to start with ADAM optimizer, and I will show you in the following videos some examples how we can code this. And then experiment with other optimizers if needed. So let's have a hands-on code using different types of optimizers and different batch size compared to the previous coding examples. In this Google Colab, I will show you how you can use Tensorflow and implement a digit classification network using some of the new techniques that we have gone through in the last couple of videos. Most of the code will be the same, but there are some changes both to the network as well as in the training process. So here, one thing that you can see, the batch size is 64 instead of 1. So we are gonna to do a number of training examples in parallel. The rest of the code will be the same. And then here the network definition. You can see how now the activation function has changed in the hidden layer. We are using ReLU instead of tanh. And then we are using the hey normal for the weight initialization. Then we zeros the bias weight. Also in the output layer, I'm using the softmax instead of sigmoid, and I used the Glorot uniform for the weight initialization, and also the bias weight to be 0. And then in terms of the training process, this is the training process. I'm using categorical cross entropy loss that goes together with the softmax function. And you will use Adam optimizer instead of the stochastic gradient descent. And apart from that, everything else is the same. You can see here we pass the batch size, and it's gonna be 64 examples in parallel instead of one example at the same time. It will be faster if you compare it with the previous code that we have used previously. And also the accuracy for both the training and the validation went up. For the training accuracy, it is about 98%, and for the validation accuracy, about 96%.